Okay, so last time, when I was talking about visual design, I didn't get to do nearly enough drawings, and so well, let's gonna do a simple thing. We're gonna design a light bulb, um, but not just any old kind of light bulb. And maybe we'll do a bunch of different types of light bulbs. So last time I was gonna get into visual design, and I guess in the end it was not about visual design. It was more about engineering, which really is more about functional design, right? There's visual design, and I think what I often don't hear about in the drawing space is functional design. How do things work? How does your idea work? And everybody seems to run into artist block. They don't know what to draw. And so I think the reason we want to get into functional design is so we don't have the artist block, and also because I think visual design is largely, well, thanks to AI, it's going in there and it's basically, anybody can type in Greg Redkowski masterpiece and then have it, generate something, and it's like it does all the visual design stuff. So functional design, I guess, is something that requires problem solving, which the AIs can only do if it's already been done before. If it's already in the data set, then it can do it. But if it's not in the data set, then it has no precedent for it. And so that's the whole point of being an artist, is to be original and make new things and do the things that aren't already in the data set. So yeah, I was thinking, how about a bug light, right? So basically a light bulb with a bug in it, as opposed to an electrical filament. Should I just do that? I don't know if I should just go into that, because I wanted to talk about conventional light bulbs in the first place. Because really, when you're doing engineering or you're doing functional design, you're stepping into the realm of world building. And when you work as a world builder, none of your designs stand alone. So an example of this would be, well, okay, let's talk about a light bulb first. All right. So light bulbs, they have, incandescent light bulbs, which are all being phased out in favor of LED bulbs now. So, eventually there will come a time where this video is so out of date that nobody even knows what an incandescent light bulb is. You have these posts, you have a filament, and actually your filament, hold on, your filament is, right, something like that. It's got a whole bunch of coil. It's got a bunch of coils, and it's coils within coils, right? And then there's a glass bulb over the whole thing. And then your rating and your lettering you might have some stuff which talks about how many amps, voltage, right? Like, and then the wattage, and it's printed on like the top of the bulb, like that. And then at the bottom of the thing, there's a kind of an insulative thing, and then there's like the conductor. So there's like a conductor on the bottom, and then there's the screw mounting, right? And so here's the thing, is that there's this screw mounting, right? There's screw threading in here. So the thing about that screw threading is that screw threading, well, it has to go into a light bulb socket, which has its own screw threading, right? So this is, I guess, it's good that we're talking about this, because I wanted to say that none of your designs stand alone, right? So you have to have some sort of socket for this thing to go into and to screw into, right? They match. And then, oh, right, like, well, there's got to be, assuming that this light bulb is something that goes, onto the wall, well, then there's going to have to be, I guess there's just going to be two terminals, right, out of the thing. There may be a ground. There may be, there may be three. There may be three leads. Certainly, if it's a fluorescent light bulb, then you're definitely going to have 3 leads. So yeah, you might have like something like that. And then, well, what's coming out of the socket? What do the wires hook up to? And so the wires probably have to, those 3 wires have to probably, well, the ground lead, might go to, some piece of heavy, metal, which eventually conducts to the foundation. This is the electrical signal for the electrical symbol for ground. Sorry, hang on. Let me redraw that. Right, so it'll look. Right, and then your other two terminals have to go. Well, remember it's AC voltage, not DC usually, and these go off to some fuse box somewhere. Right, your fuse box. Somewhere in your basement, you've got a fuse box or circuit breakers. And then you have all the different breaker switches. And of course, in your fuse box, you may have little labels that actually say, this is for kitchen light, and this one's for like the stovetop and that sort of thing, right? In fact, you may have several several lights which are all hooked up to one single breaker. So if you have enough things connected to that one breaker, all in the same circuit, you might overload that breaker, and then the breaker will trip. Or if it's a fuse, you'll blow the fuse. Interestingly enough, the fuses have the same screw type mounting lugs as the bulb does. So all this stuff goes off to a breaker box, and you might have several light bulbs in parallel, right? So they won't be in series, right? So something like this might have another light bulb, and so on, right? Like something like that might also have another light bulb. If you know anything about circuitry, then and wiring and stuff, you need to know how this stuff works, right? And this is in parallel, right? In parallel means you've got two lines. I won't say negative and positive because it's AC current, alternating current, and then one of these leads goes off and goes into each bulb like so, right? This is a parallel circuit. So the thing about doing any kind of functional design means you got to know, like, the more science you know, the more like science and tech that you know, the more of this kind of specialized knowledge. In this case, this is knowing how electrical stuff works. The more of an advantage you have. So this is a parallel. This is a parallel circuit. And then a series circuit is like Christmas lights. This is where you have something like this, where you have one going up like that, and then the next one goes like this, and the next one goes up like this, and so on, right? So the thing about functional design is we don't care how things look. We care how they work. And so, and inside the bulb, remember, right? You got that little filament here. And so, naively, this is how it goes, right? This is all one long wire. This is one long conductor. And the problem is, if one of these things blows out, if one of those filaments breaks, well, then the whole circuit is just going to break. All three of the lights will just go out, and then you have to figure out which of those bulbs broke. That's why we often don't use hookups in cereal. This is cereal. No, not the cereal that you eat at breakfast. That's a serial circuit, right? And then this stuff all goes back to the fuse box or battery or what have you. Right? That's a parallel circuit, serial circuit. Whereas with a parallel circuit, in this case, if one of them goes, only that one goes, and that's fine. Like, the others will still function. And of course, when you do a serial circuit, if you have, let's say, 12 volts, right? If your battery is 12 volts, well, then you're not going to get 12 volts. You're going to get 12 volts that is basically spread out over the entire circuit. So each one of these is getting 4. This one's going to get 4. That one's going to get 4. That one's going to get 4. So they'll get dimmer. The filaments won't glow as brightly. They'll only be getting 4 volts each. It gets split up. That's a problem. That's another problem with serial. Whereas if you're dealing with something like a parallel circuit, if you're running 12 volts in parallel, they're each getting 12 volts, 12 volts, 12 volts, and your amp draw would be tripled as a result of having 3 of them in parallel like that. And the thing is that because the amperage draw, which is the amount of the amperage is like the amount of electrical flow, the amount of current flowing, the amount of power or energy being drawn. This is why if you put in too many bulbs in parallel, the load on your circuit breaker, which is a little piece of bimetallic resistive metal, if you have too much current flowing across it, it's going to get hotter and hotter and hotter. And when it's overloaded and too hot, then it breaks the connection to avoid causing an electrical fire or something like that. You don't want to have too much heat being generated. That's what causes electrical fires. So the point of a circuit breaker is to have or a fuse is to have something in there, a weak point, a designated weak point that is only going to go off here in the circuit breaker box, right? And so when you put too much crap on the circuit, it overloads that weak point. That circuit breaker trips, and prevents any kind of electrical fire, right? If you threw a toaster, if your toaster falls into the bathtub or something like that, and it suddenly starts drawing too much current because it short circuits, then that circuit breaker, or usually if you have a GFI, like a ground fault interrupter outlet, a GFI or GFCI outlet in your bathroom, those are supposed to be GFCIs. If water were to get into one of your appliances, it will short it out and it will trip the breaker at the outlet level. So your outlets, you ever seen those outlets, right? The outlets that have the 2 sockets like that, and then they have these little 2 buttons, right? They have like one button for resetting and another for testing. Yeah, that's those are the GFCI outlets or GFI outlets. And so yeah, you'll have, right? So, right, knowing, the more you know about electricity, the more you know about the actual fucking thing, the more it informs your design. The more you know how it looks like, right? This is what artists do. Artists draw. And what drawing is drawing is figuring out what does it look like. And if you want to know how it looks or what it's supposed to look like, then you need to know how it works. And so that's why I'm going into conventional light bulbs right now, because I think a lot of people don't fucking know how this stuff works or what this stuff does, which is not a crime or anything. It's just they don't teach this stuff, right? Nobody teaches this stuff. I can see that one was incorrect there. That looks better, right? And so this stuff, well, I mean, it doesn't just end at the circuit breaker, right? Well, this is usually what everybody sees, is just they see the circuit breaker. And then, well, your circuit breaker usually goes to some kind of, main, you've got some kind of, Frankenstein switch, and the Frankenstein switch is used to shut off all the power, right? Like, you got a kind of a main switch if you needed to shut off everything at once. And then this thing goes off to, well, I mean, usually outside of somebody's house, they'll have a power pole, right? They'll have a utility pole outside. And the utility pole has, oh, actually, usually people's houses do not hook up directly to a power pole. No, we're not going to skip anything, all right? We're not skipping any details, right? Because again, every time you know something new, if you know something new, then you have something new to draw. And believe me, the more you know about this stuff, the less you'll have problems of drawing slumps. The less you'll have an artist block. And an artist block occurs because drawing is a conditional thing. You haven't satisfied the conditions necessary to output a drawing. And usually the problem is you don't know what to draw because you don't know how the thing works. And so, you just say, oh, I don't know why, I need inspiration, right? And so knowledge is, knowledge of a thing and the fascination of how the thing works serves as a form of inspiration to kind of tell you, oh, hey, that's kind of cool to me. I want to draw that, right? Yeah, that's kind of neat. Right? This is why every so often, there's always some new fad that goes around on Twitter, and everybody suddenly wants to draw it because they never thought of the thing. It's like, oh my god, feet! Oh my god, and suddenly everybody's drawing feet. How it is. So yeah, I guess outside of your house, chances are what you'll have is something that looks kind of like this. You'll have a bunch of these little weird ceramic, porcelain insulators, something like that, right? You have one of these little jobbies outside. And so I guess, that's what your main line connects to. This is going to be on the side of your building. And then these guys will go out to the utility pole. And the utility pole has a bunch of things. It's got that weird T shape, right? And then maybe a bird is taking up residence inside your power pole. And then you have this thing, right? You got this big freaking can, right? Sometimes you'll see these big freaking cans, and then, and then the utility pole has the porcelain insulators as well, right? They use ceramic porcelain because they don't want to tie the wires around the wood directly, right? Or concrete or whatever these things are made of. And so, yeah, you might have one or more of these cans attached, and so yeah, that these cans are attached to that. And then then the can might have some other sides to it. You know what? Let's actually look up one of those power pole transformers. It's so let's see, power pole transformer. These are the things that sit outside your house and they buzz. Oh, okay, so that's how they look. Ah, wakarimashita. So desu ka. Naruhodo. Okay, hang on. Yeah, I've made. So this is the thing, right? If you don't know exactly how it looks, look it up. Right? Do some research. So they have another kind of ceramic insulator on top, right? And so that is what hooks up to your other ceramic insulators, which may have some standoff, but in this case, we're going to simplify. And then on the outside of these things, they have a bunch of nipples on the outside of them, and then the nipples will have, those will connect to your house lines like that. Now, what a transformer does is, well, if you live in North America, chances are you've got 120 or maybe 110 volts AC, 60 hertz. Right? But your transformer, I don't know how much they crank those things up to. They crank them up like a lot. Let's see how much. Oh god, they have like single phase and 3-phase, and oh my god, wow. Okay, yeah, there's some really crazy fucking diagrams with really you want to see the most complex power poles? Look up the ones in Japan. If you've ever been to Japan, you ever been to Tokyo? Oh my god, this serious, the amount of crap that they put on top of a power pole is impressive, seriously impressive. And there's so much detail to draw. And people people will, whenever something's detailed, they'll go, oh wow, how detailed. Oh, rah, 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 right? And I'm like, well, okay. But the thing is, the detail is all functional detail. It actually does something. It actually means something. And so, seriously, look up, just look up power pole or distribution transformers and look up power poles, and some of these will actually tell you what all these different things are, what all these different wires coming off of it, and stirrups and hot clamps and cutouts and fuses and primaries and secondaries and service neutral. It gets really deep. Okay, there's a lot. There's a lot of shit that can be hooked up on a power pole. And again, the more you know, the more you can draw. Okay, and so, holy crap. Oh my god. I just went on an image search, and there's just a tremendous, there's a tremendous amount. So let's see. I'm seeing something that says 100 kVA. Oh, so 100 kVA means it's 100,000 volts? No, 15 kVA, 25 kVA. Wow. So it really, they are talking like really high voltage, like 100 kilovolts. That's like 100,000 volts on some of these pole mount transformers. Some of them are 15 kVA. Oh, okay. So it says 15 kVA, 25 kVA. That means it steps it up or steps it down between 15 kilovolts and 25 kilovolts. And okay. So this guy. And when they're talking single phase or triple phase, and so, okay. So inside a transformer, right? Like they have, what they do is they take, they have something that looks like this, right? They have like that, and then they have like a coil winding, right? So you've got one coil, and they have a few windings that go around this kind of metal core. That's what this big rectangle is. And then they have a few windings that go around many times. And so this thing makes, well, because it's AC, that means that the magnetic field that comes off of this electromagnet, like this is basically, this is one half of an electromagnet, and this is the other half of an electromagnet. And if you, well, the thing is that if you have more windings around there, I think what that causes, it causes your magnetic field to be more dense. You have a denser magnetic field, whereas if you have only a few windings around, then you have a less dense magnetic field. And the thing is this works by way of induction, right? So I guess if you, well, I know that you're going to have a magnetic field that expands and contracts, right? And since one side doesn't have any, is not charged, the other side is charged, that as those magnetic field lines expand, they will pass over these wires. They'll cut over those, the other coil, and it will induce a current. It will make voltage start flowing on the other side, and it will basically kick back against this other. As you induce a current on this line and you're causing electricity to flow, this line will also induce and create its own magnetic field. That magnetic field will kick back and provide a counter force. So you're not getting electricity for free. You're not getting like free electricity. The other coil creates its own magnetic field, which pushes back against it, and that causes a current draw on the other side. Nothing's for free, okay? No free energy in these things. And also the voltage on one side will be less than the other. And there are electrical formula. And so the electrical formulas that you'll see, like they're mathematical, and they can figure out exactly how many turns you need on each side in order to step up or step down the voltage by a certain amount. So, oh wow, I'm like reading this webpage, and they say common sizes include 10 kVA, suitable for 1 to 2 houses, 25 to 50, typical for small buildings or multiple homes, 75 kVA and above for commercial and small industrial applications. So yeah, basically the kVA of your power pole transformer stands for kilovolt amperes, a unit of apparent power. Oh. Huh. Okay. So I don't think they're exactly running that many kilovolt. That's simply a unit of power, a unit of apparent power. Okay. So I guess it's they use that instead of like wattage. Okay. But yeah, the thing is that, remember, right? This stuff here, like whatever's going onto this utility pole, right? This utility pole, again, this goes somewhere. This probably goes off to, off down to a series of other fucking utility poles. And eventually it goes over to like, a substation, right? And the substation has like a whole bunch of fucking, transformers and crazy ass stuff, right? And this substation is also like the transformers. Remember, the transformers step things up or step them down. In this case, there'll be step downs. And then these guys go off to some big freaking, well, you've seen these towers, right? Like, the big freaking mega towers, right? Right. And then your mega towers, they go off to, the generating station. And so your generating station would be, well, I mean, the generation station probably has its own set of transformers, which sets things up even more. Or actually, yeah. So what you have is your generation station is usually you're going to have some kind of turbine. Your turbine is going to be, coal or nuclear or hydroelectric or solar or whatever the fuck it is, right? And even then, it might not even be a generator. It might just be hooked up to some other distant transmission station somewhere else, right? Because what happens is usually you need to have some sort of generation central, like something which actually generates the electricity, and then there's a huge distribution network which goes and it breaks it. These go off. Sorry, we send these off to other distribution points, and then those distribution points fractalize offwards, and they branch into smaller and smaller distribution points. And it serves, if you're going to send electricity over long distances, you want to increase the voltage. You want to step it up like crazy because, like things with high voltage travel better. Like the higher the voltage is, the better it travels. And what I mean by travels, it means like, well, your wires are not superconductors. They have resistances. So there's, lightning. Lightning is what is the voltage of a lightning bolt? Okay, what's the voltage of a lightning bolt? What is the voltage of a lightning bolt? Okay, let's see. The voltage of a lightning bolt varies significantly, but is generally estimated to be between 100 million and 1 billion volts. And I'm doing the Dr. Evil thing right now. Like that's a lot. Extreme cases can exceed 1 billion volts. So remember, with a lightning bolt, right? Lightning bolt, that means you've got some cloud. You have electricity from the cloud, which is doing the whole, woolly sweater, cat, balloon, doorknob, fucking static electricity parlor trick where it generates I won't say 1 billion, but let's say 100 million at the low end. 100 million volts, and it's able to push an electrical current from the air to the ground. All right? And I don't know how high a storm cloud is. We can ask. Let us ask the internet. What is the altitude of a storm cloud? A cumulonimbus cloud can be anywhere from 60. Let's see. Typical is 12,000 meters or 39,000 feet, and 20,000 meters, 66,000 feet. Extreme cases exceeding 21,000 meters. A long way away. So like we're very, very far away. And so a thunder, like a lightning strike can hit the ground from, at the lowest case scenario, 12 kilometers away. All right. And it's going through air, moist air, mind you, but it's going through fucking air, not a typical thing we call a conductor. All right. So the thing is, air, we call it an insulator, but anything that electricity can go through suddenly becomes a conductor, right? As long, because it's conducting electricity is going through it. All right. So the thing is that this thing can go through 12 kilometers. I don't know what 39,000 feet is in miles. Let us find out. What is 39,000 feet in miles? 7.3 miles. Okay, in freedom units. 7.38 miles. That's pretty far, okay? And that's through of air. Okay? So when you take voltage and you transform and you step it up and step it up and step it up, it can go through something like air. So it stands to reason that if you're generating electricity, that if you step it up high enough, it will go and slice through your long distance transmission lines. And then when it gets to your house, well, I'm sorry, we don't want our electrical devices blasting us. We don't want to get blasted by our refrigerators and our toasters. So we step that shit down. We step that shit down so it's safer. And we step it down and step it down and step it down until it's like a mild 120 volts or 110 or it's like, maybe 240 if you're in the UK. Or in Japan, I think it's like around, it's 110. I think the appliances are compatible between Japan and US and Canada. Yeah, and so we step that stuff down so we're not getting shocked by our home appliances, right? This is why we step it down, right? So the reason I'm talking about all this science shit, even though I'm not drawing, is because this stuff explains why do we have giant fucking transmission lines? Why do we have all this stuff, right? And it's like, if you want to make anything fictional, you should first understand how real things are first, so that you have some kind of basis of comparison, right? If we're not transmitting electricity and we are instead transmitting magic, well, then maybe magic has some kind of voltage and amperage. Maybe magic can start following the rules of electricity, or maybe we're dealing with lightning magic. Okay, that's what that's what all this electricity stuff is. All right. Now, getting back to the light bulb. Okay, look. You're gonna have to appreciate the fact that yes, we are gonna get into these detours, side quests, right? Detours and side quests. And the thing about the detours and side quests is that, people are like, oh no, I have a drawing berry. I've got the drawing block. I don't know what to draw. I'm out of ideas. And I'm like, well, once you start really studying things, you have a zillion things to draw. You have the opposite problem. You now have an overwhelming number of things to draw. Right, like that's the thing, right? This is functional design. When you get into functional design, you have an endless number of things to draw, and an endless number of things to figure out, and an endless amount of creativity. Let's get into the light bulb, though. Let's talk about what is really going on with light bulbs. How does the light bulb even get made? How does it even come out of the fucking factory? It's like you've got a bunch of things. You have the glass. You have this glass bulby thing. You have the metal or brass. Usually it's like, I think it's some kind of brass cup, the socket cup. You have things like there's some kind of resin black insulator thing. So I guess this resin black insulator thing is used to, that means that so if we have these two terminals and then we have the filament which goes in between like that, naively, one of these is going to be connected to the brass cup, while the other terminal goes to that other nipple, right? It goes to that other terminal, the other nipple terminal at the bottom of the I just like saying the word nipple. It just goes to the nipple part of the other terminal, right? So you have your brass outer terminal, then you have the inner terminal or central terminal, and then you have an insulator of some kind to separate the two so the thing doesn't short out. And then I remember a bunch of other things like this, the filament is made out of a very special metal called tungsten. And tungsten, the alchemical, the atomic symbol or the elemental symbol is W. I think, I know that tungsten is mined from a mineral called wolfram. But, tungsten also kind of, if you ever forget, which one it is, it kind of looks like the light bulb filament, doesn't it? All right, so that's tungsten, right? Tungsten comes from, and tungsten is like this very, very expensive, very, very dense, very, very, very hard and resilient metal. Like they use this stuff in like armor piercing ammunition. And light bulb filaments, because remember, like, this is an incandescent light bulb. An incandescent light bulb incandesces. Incandesce means the thing heats up so much, it gets so freaking hot, it starts throwing off light. And the problem with incandescence is that if you do this in regular atmosphere, things will oxidize very, very fast. It's kind of like it burns, right? The stuff will burn. So the thing is, you can't just have air inside your light bulb. You got to purge your light bulb. You got to get rid of any oxygen. Oxygen is going to screw that stuff up. But if you just sucked all the air out of your light bulb, then you're going to get, basically a lot of atmospheric pressure, pushing from the outside, trying to implode your light bulb. If you just had pure vacuum in your light bulb, your light bulbs would be very fragile. You just tap them and they'd go, pew, they'd blow up. That's a problem. So what they do instead is they put in some kind of chemically inert gas, a gas that just doesn't burn very much. I don't know. Let's see. What are the uses of fill here? This is why we have the internet. Okay, we're living with. We all have cell phones which have connections to the internet, and so it's like, okay, what is the gas filling an incandescent light bulb? All right, no excuses. You have to ask these questions because it's easy, very easy. Argon, ARGON, argon. 73% argon, 7% nitrogen. And it prevents the tungsten filament from oxidizing and slows down its evaporation at high temperatures, significantly extending the bulb's lifespan. Other gases like krypton and xenon are used in specialized or higher efficiency bulbs due to their higher molecular weights, which further reduce filament evaporation and improve energy efficiency. However, they're more expensive and less common in household bulbs. And the LED bulbs don't have any gas. Okay, so argon and nitrogen. Okay, so the thing is, these are all chemically inert gases, which typically do not cause your light bulb filament to burn. So AR and nitrogen. One of these two gases. So what they do is they push these gases in here to push out any of the typical oxygen stuff. Oh, and they often use one other thing they do is that I remember reading somewhere that before they assemble this whole fixture, this whole thing, they will dip the filament in a kind of lacquer, a specialized lacquer. And the lacquer includes something called a getter, a Getter. It gets things. What the getter does is, prior to them shipping the light bulb out, they'll test the light bulb. They actually turn the thing on. And during the testing phase, when the light bulb turns on, the getter burns on the light bulb and it gets the oxygen. It gets any remaining oxygen out of the bulb after they purged it. So the getter gets all the rest of the oxygen. Right? And then, that way there's no more oxygen anymore. It's all been consumed by the getter. So, you'll notice, right? It's like when I talk about a light bulb, right? Like, you just realize how rich all that infrastructure, all that stuff that is necessary for making light bulbs a thing. Okay? This is when you do functional design, you get into world building. All right? World building becomes a part of your design process. None of your designs, none of your ideas stand alone. They're all connected in some way. So if we're going to get into the bug bulb, this is why I didn't want to just get into the bug bulb right away. Right? So the bug bulb is basically, it's a bulb. There's a bug inside. Oh, right. I guess the bug has some kind of light butt. It's got some kind of light butt, right? All right. We're gonna say, why a bug bulb? It's so that we can do away with all this other shit, right? Right. We don't want to have to deal with all that other crap. We want a standalone bug bulb, right? Isn't that great? Standalone bug bulb. We're done. Let's just go home now. Well, don't bugs need air to, don't they need to breathe? Isn't the poor little guy gonna die? That's kind of a problem, right? That's kind of a problem. I mean, okay, well, why don't we just separate off his butt? We don't need the rest of the bug, right? We'll just keep his butt. Well, the problem is the butt doesn't just give us, the biochemical. It doesn't give us the bioluminescent compounds for free, right? Like the thing about the bug is actually kind of useful. The bug eats you know, it eats stuff like honey, or it eats like sugar, or eats some kind of food, some kind of nutrient, and it turns that nutrient into the necessary biochemicals, right? So, but the other problem is bugs poop, right? So, sorry, I'm just trying to make a little poop emoji here. I I mean, it's kind of ironic having a bug which poops, and the bug poop has its own bugs. This is why functional design is so much fun, right? Drawing's got to be fun. Okay, drawing has to. God, I keep hearing about people who draw who get burned out because their ideas don't give them anything in return. All right, your drawings have to give you something in return. There has to be some sort of sense of wonder that comes from drawing. There's got to be some sense of satisfaction that comes from drawing. Like, oh my God, I made it work, and now it's convincing, and it's kind of cool because of that, because it's original, and I made this, and I'm proud of the ideas I came up with and threw into this thing to make it work. That's an important part about functional design, is because you're not just thinking, how do I make it look cool? Everybody wants to know make things look cool, and they always, and they're all like, well, let's just do whatever's trending, and so they all just draw like Mimpembo porn, right? Because that's what happens. Is in the end, if all you want to do is draw what's cool and popular, and be a Twitter, artist, and an Instagram artist, eventually you're just going to have to follow the whole pipeline until you're doing nothing but drawing Mimpembo porn. And that's kind of a dismal. That can be a dismal existence. I mean, look, if you're enjoying it, great, good for you. Good for you. But for the rest of you whoever wanted to be, whoever wanted to get into art because you wanted to make movies and video games, you wanted to be like, the guy who comes up with the whole like IP and everything. Well, that's kind of that's probably not what you had in mind, is it? So, right. The problem is the bug poops. That's a problem, right? The bug poops. The bug needs food. The bug needs air. These are all problems, right? And the whole point of this is to make a self-sufficient lamp. And maybe the thing is, we're not, and we're going to use these to replace light bulbs. We're going to go and go around and we're going to screw these bug bulbs into every single fucking light fixture and lamp and like wall mounting and so there's some problems, right? Right, and it's okay. Remember, the problems are there to be solved, right? He needs air. Right? He needs air, food, water. Then there's the poop problems. There's the problem of the poop. Right? So fine. Air. We make little air holes. We give him some air holes. So the poor little guy can breathe and he doesn't suffocate. They got to be small enough so he can't get away, though. All right. Okay, now the other problem is the food and water, right? We could give him like, here, maybe what we'll do is we'll put the air holes kind of in the middle, because the problem is that like I want to put the food crystal, like, he's got enough food. Let's just say, for argument's sake, that this is some kind of super hyperfood, right? Some amazing hyperfood for the bug to go up and he can lick it. And eat his delicious superfood, and make bug light for all eternity, right? And the superfood lasts a really long time. Oh, and maybe the superfood even has water, right? Or maybe like the superfood has like, maybe instead of just the superfood, it's got like a little, like the little hamster, the little hamster gerbil water bottle, right? And he can lick that. And maybe what we have is, we can have like another, right? We have like another drinking vessel. This is basically a lifetime supply of superfood and or just bug water that he can lick, and it will last him for his entire life. And he's got air. And the reason I wanted to put the air holes, well, actually, not the air holes can actually be kind of towards the top. That's fine, right? We'll just take those. We could even make it so that the air holes, the air holes can be, yeah, actually, no, yeah, well, we'll just drill them through the top. We'll just pepper them around the top like that. All right, there. Okay. All right, that's fine. He's got enough air to breathe. He's got food and water, right? So that's good. That's good. Now, what about the poop problem? Well, I mean, one thing we could do is we could make it so that the whole thing just has a little poop trough at the bottom. Okay, we can make a poop trough, and the poop just gathers up, and so he has enough space for a lifetime supply of poop, right? As long as that poop trough is the same size as the bulb, right? Then theoretically he's just, when the thing empties out, it's just going to run out of food, and it's going to convert into poop. So we got a poop trough, right? That's one way to do it. Maybe the other way to do it is we can handle it like oh, here's an idea, right? We can do it like the way the aquariums do it, right? Aquariums have like little snails, right? They have like little cleaner snails. And the snails like to eat poop. I don't know what happens to their poop though, right? But I mean, they're good at eating up poop. But I don't know, maybe somehow the snail poop is less of a problem. Maybe it just smells less. So maybe that's the thing, right? Is that now there's like a small ecosystem inside this bulb. That's kind of cool, right? It's like, oh wow, it's like the bulb is more like a tiny little ecosystem for our bug to live in. And it's like an encapsulated disposable ecosystem that provides light, right? And the thing is that, like, to what degree will you scale this thing, right? So you're going to say, well, will this be a one-off lantern that maybe your character carries around with them, like a gas lantern that they carry around, and then occasionally they'll swap out the juice bulb, and they'll occasionally open up the poop trough and they'll empty that poop trough out? Will this be something that is deployed at scale in many buildings and in institutions? Right? Because this is the big question, right? Because once upon a time, a lot of in-house lanterns were oil lamps, and people had to go around and light the fucking wicks on those things, right? And yeah, it was a pain in the ass, and it was also very hazardous, right? It's like those things were constantly starting fires, right? You knock one over, the thing's full of fuel, it's full of oil, and it's got like a little wick and a flame, and and believe me, I was like, yeah, it wasn't very, it's kind of a problem, right? So that's why I guess the bug lantern's a lot safer, right? It's like if your bug lantern breaks, well, then the worst thing that can happen is the little bug, flies away and runs off, and that's not that big of a deal. So it's much safer than the oil lantern, and of course it's self-contained and all that. Whereas the oil lamps, I mean, what they do, they had fucking whale oil lanterns, right? And they had to have the whale oil lamps. Well, they used whales, and they had an entire economy based around whaling, around hunting down massive mammalian sea creatures. They had to go out paddling out. They had to go out in sailing ships with little paddle boats and harpoons, and they had to go out and stab and drag back gigantic mammalian blubbery creatures. And then they, harvest them for their meat and their blubber and their oil and their ambergris, and which was used in perfumes, and it was they would make an entire economy around these whales, around whaling, and which they had oil lanterns and whale cosmetics and whale everything. Like everything was made out of the whale, which is kind of interesting, right? So it's like when you look at things like a lot of, like, let's say native or Aboriginal cultures, they would hunt something like a buffalo, right, or an elephant, or they kill some giant freaking creature, and they harvest the thing, and they get the ivory out of any horns or tusks, and they get a whole lot of meat and fat, and they get fangs and claws, and these things are all useful to them. They get the hide and the fur, and like they find a use for all of these things, right? It becomes integrated in their entire life Their entire lifestyle is built around this one creature. And if this creature was gone, like if the creature moves, then they got to move with it, right? The thing's nomadic, and you know, if the weather gets worse, the thing goes off to greener pastures somewhere else. They got to go with the damn creature, right? Or they got to, you know, somehow store up enough supplies and hunker down for the winter, if they're living in a place with seasons. And so this is, you know, why the functional design is what allows you to be, this is what gets you past all the problems of oh no, I don't have enough ideas, right? Because people who run out of ideas, they run to ChatGPT to make, you know, to decide all these things for them, right? When they don't realize that actually, you know, these ideas actually come to you very easily, when you start thinking about, well, what are the details of how the bloody thing works? And I mean, look, you know, you absolutely could use, you can question you can ask these questions of the ChatGPT. You know, you can ask the questions of your AI and whatever, and ask, you know, how would I feed this light bulb bug? You know, and you can ask the thing, all right, and it will give you answers, and you can use that to then you draw it out, right? You can draw it out, or you can ask it to go and make the images for you. You know, if you suck at drawing. But the important thing is at least there is some aspect of intervention, right? You're involved in the process. You're asking the questions and you're selecting the answers, and you're spending your whole day. You know, as long as you're spending your whole day having to do something, such as thinking about the thing and organizing everything, hey, that makes you, you know, that's the creative part, right? Because you're ultimately the one who has to drive the thing forward and see it through to completion until it becomes a comic book or becomes a movie or an animation or something, right? You're a world builder now. You're an actual designer now. So, yeah, I hope this. Remember, you're always going to be trapped in endless side quests. All right, that's the nature of the gig, but it's endlessly entertaining. It's all that, right? You know. Mostly I talked about the light bulb, right? But it's just, yeah, you're going to be in many side quests. And if you find that interesting, well, then, you know, maybe being a creator is for you.